three factors. The definition of coefficient didn't change. It's got to start with 3. What separates factors? Multiply, divide. Okay, so basically multiply. So if it has 3 factors, that means there has to be 3 things multiplied. Does the 3 count as one of those 3 things? Yes. Because it is something being multiplied. So I just need to put 2 other things here to make sure that there's 3. 3 times x times y will work. Do you have to use x and y? No. As long as it's some variables. You could put 3ab, 3bh, 3zz, or gy. Doesn't matter. As long as it's 3 times something times something. Alright, so that one's taken care of. 1 has 4 factors. This one doesn't specify anything other than there has to be 4 factors. Right? Factors multiply. I have to multiply 4 things. So if I want to, I could just multiply A, B, C, D. That works. I could put a number as one of them. Like I could put 3 A, B, C or something if I wanted to. But it doesn't specify that I have to have a number. So if it doesn't specify, I don't have to do it. I just have to do what it says. So there, I got that. I got some with 4 factors. Last one is constant. What does constant mean?
Just a single number.
Just a number. So constant means, let's say, 127. Right? Just any number, as long as there are no variables. As soon as you put a variable in there, it's not constant anymore. Number 1 makes sense.
Wait, you could label them, like, each one, which one is which, you know? Or on the top?
They're in
I'll
order.
kind of explain it.
They're in order.
Okay,
So,
okay.
first one is coefficient of 3 with 3 factors, 4 factors, constant. They're in order for the list. I just went in order.
Okay, but I'm confused. Why does, like, 4 have an X by it if it just says...
Because it says has a coefficient of 4. Coefficient, by definition, is a number multiplied to a variable term.
Okay.
So it has to have a variable at least. Now, you can put more than that, right? This could be xy or xyz, or as long as there's a 4 in front. If you just put a 4 though, that's a constant term. It's not a coefficient. Does that make sense?
Yeah.
Yeah. Part of being a coefficient is that it's multiplied to variables.
Okay.
Does that make more sense?
Yeah.
Right. It's the same thing here. 3 has to be a coefficient, and it has to be 3 terms. And that 3 factors, that's why I have 3 things specifically. Over here, it doesn't matter. Here it does because it specifies 3 factors. So 3 things have to be multiplied. So I have a 3 in x and y. I have 4 in that one because it says 4 factors. So it's 4 things multiplied. And then constant would be just the number. Does that make sense? Okay, second one is probability. That's been a big choke point in a whole bunch of classes. So it's not just you guys. But we're going to keep practicing it until we get it. Alright, deck of cards contains 10 red cards, 15 blue, and 5 green. If you pull 3 cards out of the deck, what is the probability that all 3 are green? So you can use the tree diagram if you want, but since you know, like, hey, there's only one thing I want, green, green, green. If you know there's only one particular thing, I can say, hey, this is my first thing, this is my second thing, this is my third thing, I want green 3 times in a row. So I'm just going to label, hey, I want green, 3 green. If I do multiple things in a row, what do I do to the probabilities? Multiply. So, the first thing I want is to pull a green card. So I'm going to put the probability here. How many ways are there to pull a green card? 5, because there's 5 different green cards. How many cards are there to choose from? How many cards are there in general? 30. So in other words, 5 out of the 30 cards are what I want. Fair enough? Now, to keep going, to say, hey, I'm going to go to the next green card, I have to assume, hey, I pulled that green card out, I have it. So if I have one of the green cards, how does that change my possibilities if I want to try to get another one? I have one of the green cards, I have one of the cards. So there's one less green card in circulation, there's one less card in circulation. Does that make sense? Yeah. So now I'm going to the third one. How does that change?
3 over 20.
There's 3 greens left because now I have 2 of them. There's 28 cards left because I have 2 of them. Does that make sense? Now, I can't do the bottom one part of my head.
24,360.
So in other words, there's 24,360 ways that this is going to work. 60 of them are 3 greens. You can put that in the calculator. I think it's 1 out of 4 of 6.
Yeah.
And the calculator will simplify that for you. So in other words, there's a 1 in 406 chance that you actually get 3 greens in a row. Not that great. But it should make sense. If I ask, does it make sense that the chance of that happening is really small? It should, because there's 30 cards, and if you only start out with 5 out of the 30 being what you want. And then each time you pick one out, the chances go down every single time. So it should make sense that the probability gets worse the more of them you try to pick out. Does that make sense? Like 5 out of 30 is not that bad of a chance. But then you have to consider, oh, then it's only 4 out of 29, then it's only 3 out of 28. My chance is getting worse and worse the more I pick out. Both of those make sense. So hopefully if you have those down the next time that I put one of those questions on there. Now when I do the check-in problems at the end of this week, you're going to have options. Instead of just me saying, like, hey, do all of these, you're going to have choices. And you'll get to pick the ones that you need to improve. So I'm going to have like multiple problems. I'm going to say like, hey, do 4 of these questions instead of just do all of them. That way you can do the new ones, then you pick from the old ones, whichever one you need to improve. So if you got a good score on this one, then don't do that one. Then you already got it. Right? But if you got a lower score on this than that, then I would pick that one if you have the choice. Does that make sense? That way everyone can improve what they need to improve, and it's not just you doing what everyone does. Okay. The next stuff we're going to go through is going to be about simplifying expressions. We've got the idea of what the terms are, factors, coefficients. We've done things with exponents. We've done things with figuring out how to identify each of those pieces. But a lot of times, when we get to later stuff, when we're going to start solving equations and start doing actual stuff with word problems and actually doing problem solving, we are going to want to condense and make things better. Because a lot of times there's going to be a bunch of junk, and you want that to condense and be nicer, and that's how we're going to do that. The first thing we need in order to do that is understand like terms. Every one of you has heard the phrase like terms. Formally, what that means is that they are terms that have the exact same variable part. The variables are the same, the powers on the variables are the same. So that's our official definition of what like terms are. The variables have to match, and the powers on those variables have to match. So we're just going to look at some examples real quick of things that are and things that aren't. Those are like terms. They both have x. Both the x's are to the first power. Now those are also like terms. Sometimes they're not going to look like it, but if it fits the definition, then they have to be. So even though it's like, hey, that's xy squared, that's y squared x, do they have the same letters, and do those letters have the same exponents? Yes. That means they're alike. They don't have to be in the same order, multiplication-wise. But as long as all of the letters are the same, and all of the powers on each of those is the same, because the squared's on the y, and it's just x. So we're good. Those are like. All constants are like terms because they follow the definition. They have the same stuff. They have the same variables, none, and the powers are the same, 1. So everything, they are alike. So we don't have to worry about numbers. Now, things that aren't. If they're not the same, we cannot combine them.
They don't have the same variable.
Huh?
They don't have the same
They
variable.
don't have the same variable. Right? A lot of times, the mistake people make is they try to combine these numbers somehow, and you can't, because they're not the same things. Even if the numbers match, or like the letters match, but the powers are different, those are not like. They have the same letters, one's squared and one's not, but the wrong one is squared. So one has x squared, one has x, one has y, one has y squared, they're different. If even one exponent is off, they're not like terms. Does that make sense? And obviously, just so we have this down, because I know what's the difference. Constants and anything with a variable are never alike. If we have something that's constant and something that's not, we can never combine them. They are not the same, they cannot combine. Fair enough?